Our next speaker is Karthik Sooryanarayana, and he's from the University of Illinois, Urbana-Champaign, and the title of the talk is Controlling Rheology of 3D Printable Concrete Through Vibration.
Hello, I'm Karthik Pattaje, a PhD student in the Civil Engineering Department at the University of Illinois, Urbana-Champaign. The title of this presentation is Controlling Rheology of 3D Printable Concrete Through Vibration. This presentation also includes the work of a co-PhD student, Chanwei Shen, under the guidance of Professor David Lang. The potential benefits with 3D printing are well known, and we have all seen structures that have been 3D printed already. But are we really ready for large-scale construction? The community is, for the most part, printing cement paste and mortar. Can these be efficiently scaled up to be real civil engineering structures? There are a lot of issues with the ink, as well as various processing issues, as listed here and discussed earlier. These are all being investigated by a lot of great research groups and some commercial companies. As Tim mentioned earlier during his presentation, some of the questions that we must answer to be able to print large-scale structures are how to print faster, less defects, how to make printable concrete more durable, and probably the most important question for commercial printing is how to reduce the cost. The answers for all these questions might just be the same: using coarse aggregates, printing concrete and not paste-rich mixes. The higher yield stress or green strength obtained by using coarse aggregates can help us print faster and cheaper. Aggregates can form a skeleton required for shape stability of the 3D printed concrete in the absence of formwork. There's a possibility of increasing the printing speed due to greater layer height. Aggregates can also reduce the amount of cement in the mixture, leading to better shrinkage resistance and durability, as well as reduced cost. Seen on the right here is an image of a 3D printed concrete structure by the US Army Corps of Engineers right here in Champaign, Illinois, one of our collaborators. This is one of the early instances of coarse aggregates being used in concrete 3D printing. However, as we all know, printing with aggregates can lead to various challenges. Aggregates can impede the flow of concrete through the printer nozzle or the pumping system, and there is a greater risk of something getting jammed. So what we need for printing is a concrete mixture that can flow through the printer and the nozzle, but is solid enough to hold its shape and weight once printed. Concrete, thankfully, can behave both as a fluid and a solid. We have SEC on one hand and no-slump concrete on the other. It's both because it's a yield stress fluid. What this means is the stress acting on the concrete decides its state. If the material can overcome the shear stress beyond its yield stress, it behaves like a fluid, solid otherwise. So can manipulating the yield stress of concrete help us print it? Concrete is a granular fluid, and granular fluids react to vibration. We know concrete vibrators are used to consolidate concrete. Similarly, compactors and conveyor belts use vibration to handle granular materials. Vibration is used to impart energy and to displace particles by affecting the particle-to-particle interaction, and gravity can move it. There's experimental evidence to show concrete's yield stress reacts to vibration. At low shear rates, the yield stress is seemingly eliminated, and it is recovered as soon as the vibration ceases. This can be clearly seen in the following video. As seen from this video, concrete has an instantaneous response to vibration, fluid-like when it's being vibrated, and no longer a fluid when it's not vibrated. There is prior research which deals with this topic of how vibration propagates in concrete. A radius of action was proposed by Banfield et al., and then later there were experimental results which gave evidence to a cone of action and not a cylinder as initially suggested. The weight of concrete bearing on grain constrained their ability to vibrate. Making use of all these knowledge related to vibration of fresh concrete, we proposed a vibration-based 3D printer where We envision a reservoir to hold high yield stress concrete, that is either no slump or low slump concrete, and a vibrating nozzle such that the vibration can help the stiff concrete overcome its yield stress and help it flow out. Once it's out, it's no longer in contact with vibration, and its yield stress should go back up and should show a more solid behavior. But how do we study the rheology of concrete during vibration? To do this, we modified an existing concrete rheometer to study behavior of concrete before, during, and after vibration. An ICAR rheometer bucket was placed directly on a vibration table and clamped to it to ensure good transfer of vibration. A stand was built to separate the torque meter from physically sitting on the bucket to make sure vibrations don't carry over and affect the results. The ICAR rheometer calculates yield stress by measuring the maximum torque required to maintain a constant set shear rate. We see here that the yield stress is proportional to the torque with a geometric parameter based on the vane dimensions acting as the constant relating them. With the modified rheometer, we were able to measure the yield stress during vibration. We see the maximum torque during vibration is much lower than when the concrete is not being vibrated, about 5 times lower in this example. The static yield stress of concrete was measured at predetermined time intervals in the study. The static yield stress before, during, and after vibration was measured. The time interval between vibration was selected to mimic a 3D printing process such that a new layer is deposited every 7 minutes. 3 static yield stress measurements were carried out during vibration in each of these vibration periods. The increase in yield stress during rest represents the time taken by the print head to come back to a given spot. There's growth in yield stress of concrete in this window. The vibration represents concrete flowing out of the nozzle. Immediately after concrete comes out, it's no longer being vibrated and the yield stress shoots back up instantly, which means it should be able to hold its shape since the original concrete has very high yield stress. To test the role aggregates have on the yield stress of cementitious mixtures, 3 mixes were tested: cement paste, mortar, and concrete mixes. The concrete mix had 3/4 inch limestone chips, and it was found to have significantly higher yield stress than the mortar mix, which had the same volume of sand. Both of these, in turn, had yield stress greater than the cement paste mix. The yield stress of the mix is reduced during vibration. This is particularly pronounced in the case of concrete. The drop in yield stress was observed to be instantaneous and reversible. At the end of vibration, yield stress is almost completely recovered. When concrete mix was tested at regular intervals without any disturbance, the orange graph here, representing concrete once it's placed, it continues to gain yield stress with time at a slightly higher pace as compared to concrete, which was periodically vibrated, the concrete within the printer. These results show incorporating coarse aggregate in 3D printable concrete could be beneficial by providing a significantly higher green strength. The higher yield stress, while beneficial for post-printing properties like greater layer heights, shape stability, and shape retention, is detrimental during the extrusion process. But the results here show vibration can help overcome the increased yield stress caused by the incorporation of coarse aggregates. Yield stress of concrete can be reduced to the order of mortar yield stress using vibration. For 3D printing, we want a high yield stress when concrete is not being vibrated and really low yield stress when it is being vibrated. To study how the granular material influences this behavior, we looked at various sand content at a constant paste and aggregate content. We observed that at low sand content, that's mix A in green, the yield stress is higher, possibly due to the higher physical interlock from the larger coarse aggregate content. At large sand content, that's mix E in yellow, the greater aggregate surface area increases paste demand and increases yield stress. At intermediate sand content with good packing and lower particle-to-particle contact, yield stress is lower. It's seen that during vibration, the yield stress decreases at all sand contents to approximately the same level. That same data is presented here, but with sand content on the x-axis and yield stress on the y-axis. Each graph represents a particular hydration age. Here we clearly see the relationship of yield stress to the aggregate content. There's a minimum at about 50%. This is something we've all seen in the mixture proportioning chapter in our concrete textbooks. There's efficient packing, And this reduces the neighbor-to-neighbor particle contact, giving us a lower yield stress. Of course, with increase in time, the yield stress at rest continues to increase, but the yield stress during vibration is considerably lower and roughly the same value. We also looked at how the vibration amplitude affects this. The drop in yield stress is dependent on the amplitude of vibration. Our vibration table had 10 micrometer maximum amplitude, and at half of this amplitude, the drop in yield stress during vibration is much lower. As can be seen, when concrete is not being vibrated, the growth of yield stress remains similar. So this led us back to studying more on how vibration is propagated and affects concrete. Prior research study from our research group studied how vibration travels through fresh concrete. We know there's a radius of influence, and moving farther away from the vibrator reduces the effect of vibration. There's a decay with distance from the vibrating source. This was tested in both mortar and concrete for various aggregate content and combinations. It was found that this radius is dependent on the jamming of coarse or fine aggregates. What that suggests is if we have the vibrating immersion rod in water, the radius would be much smaller than when we have it in concrete. Concrete, being a granular fluid, is a hybrid between a liquid and a solid. To test how this translates to depth from the vibrating source, we secured a mold to a vibration table and then placed ceramic accelerometers at 1 inch, 2 inch, and 3 inch distance from the vibrating table. We tested cement paste, mortar, and concrete in this mold. The y-axis here shows the percentage of vibration amplitude as compared to amplitude at the bottom of the mold when it's empty. Vibration at different heights, that is distance from the vibrating source, was measured. We see that with distance from the source, the amplitude of vibration reduces. The effect of time is mostly negligible. What is interesting is the effect of coarse aggregate. We see accelerometer recorded greater than 100% amplitude close to the vibrating source in the concrete mixture. Depth dependency can be seen, especially at early ages. Granular behavior, the presence of coarse aggregate and its weight acting on the granular material enhances the effect of vibration on concrete. To model the flow of concrete, my colleague Chanwe used smoothened particle hydrodynamics. As mentioned in a talk earlier, SPH can model granular fluids. It considers the influence of neighboring particles and can effectively show us the behavior of granular materials. These simulations from the modeling process show the future direction of this work, where we'll bring the experimental work into our modeling to help measure physically measured properties. As can be seen, greater yield stress leads to better shape retention, and hopefully vibration can be a tool to manipulate the yield stress to help us with 3D printing. A rather simple prototype was developed based on the ideas discussed so far. A vibration motor was used to vibrate the nozzle to manipulate the rheology of concrete. Due to the high yield stress of the concrete, it's possible to print greater layer heights, and the printed layers have better shape, stability, and retention from our limited study. This could lead to faster printing and will be explored more in the future. Coming to my conclusions, in this study, a new approach to concrete 3D printing is being explored. The benefits of incorporating coarse aggregates in 3D printable mixtures and material delivery by vibration is being studied. By using coarse aggregates in 3D printable mixtures, the yield stress increases considerably due to packing and interlock of aggregates. Our hope is that the higher yield stress will improve printing parameters such as shape stability and retention, and also allow for faster printing. By using vibration, the yield stress of concrete can be overcome. This drop in yield stress during vibration is immediate and completely recoverable. By using vibration in the placement process, high yield stress of concrete can be manipulated for material delivery. Thank you.
Okay, thank you, Karthik. We're open for questions here. Yeah, what was the vibration frequency used in your study, and what was the basis for selecting the vibration amplitude and frequency?
The frequency in this study was 60 hertz. The basis for selecting initially was just we were limited by the frequency and amplitude of the vibration table we were using. And we hope to use different vibrators in the future to get a better idea of how the vibration frequency and amplitude can affect concrete. It's a work in progress, and hopefully I'll have an answer for you in the future.
Question? Let's see. Oh, yeah. How does the layer interface look like on extruded filaments? Is there adequate layer intermixing?
Yes, that's a great question. So again, I have limited experience with actually printing these mixes because of what I have in the lab. And so far with the prototype, what I've been printing is there's really good layer intermixing, because as the concrete comes out, there's still a liquid layer and when it's coming out of the nozzle, and as it sits on the next layer. So there is pretty good layer intermixing.
Let's see. I'd like to actually ask a question. What is the relaxation time for the system to go from the more viscous behavior to the stronger yield stress? Is it like a few seconds?
It's instantaneous. So what I have been doing here is, in these graphs, once I stop the vibration, I measure the next yield stress 10 seconds later, and I've been seeing really good recovery of the yield stress once the vibration is stopped.
So that gives you an estimate of, say, like if you were going to repeat a layer, you have to wait at least 10 seconds to go over it again. Or
yeah, but we're being more realistic that the print head to come back to a same location will take some time, assuming we are printing the B hut that I showed from Searle. Coming back to the same location will take 10, 15, 20 minutes, and there is an increase in yield stress during this time.
Okay, next question. How do you prepare the sample in the rheometer? Do you vibrate first and then do the yield stress measurement? I'm particularly looking at a comment on the air content during the first measurement and how much a change in entrapped air content changes measured yield stress.
Yes, I do vibrate it before my first measurement. So my idea is, if this is the first layer being deposited and then looking at the yield stress, before that, it would be vibrated in the nozzle to actually be placed. So I mimic that by actually having a pre-vibration period here for 15 seconds, and I've kept that constant, and that is how I am looking at keeping the rheological history the same. And the study that I quoted here looked a lot at how air content is affected by vibration. And obviously with vibration, we lose a lot of the air. Does that answer the question? And how much change in entrapped air content during? So I haven't yet looked at how much entrapped air content is lost because of the subsequent vibration, because the idea is each concrete is being vibrated once, and once it's placed, it's no longer being vibrated. So that's the idea.
Good. Would you please comment on preventing local bleeding and segregation due to vibration?
Again, the actual concrete being placed is being vibrated for a really small time. It's only when, so the concrete sitting here is not really being vibrated. Only when it's within the nozzle, we plan to vibrate it. So it's not being vibrated for extended periods of time. And we all know a good mix design can take some vibration without actually bleeding and segregating instantly.
Okay. Then the next question, so far, which coarse aggregate size range are you using for printing?
So in this study, we are looking at limestone chip with a maximum aggregate size of 3/4 inch. And then everything below that size was used. We could go for larger sizes, but we'll need a greater, my assumption right now is we need greater vibrational energy and a larger nozzle. Right now, the prototype I have has 1.5 inch nozzle, and half the size maximum aggregate is what we're using.
Okay. There are a couple questions here. Maybe you already answered this, but they're concerned with segregation and your observation of it.
Yeah.
Would you repeat your reply to that, or
Sure.
outline
So
that? Yeah.
the concrete mix I'm using in the study is heavily influenced by the ideology from Searle. As Pete mentioned in his talk earlier, so the concrete I actually used here is a straightforward concrete, which has no chemical admixtures at all. It's just 40% cement paste, some sand, coarse aggregate, and water. So our idea is adding any kind of chemical admixture will only make things easier. And if you can solve this idea with just basic concrete, which has good, a really good normal concrete, which is not prone to segregation easily, the risk of segregation is pretty minimum because, again, the concrete is not being vibrated continuously for a really long time. It's just when it's about to leave the nozzle that it's getting vibrated. And this is not a unique idea or anything. We have some recent papers coming, which came out from Australia, which has also used vibration, but in mortar for 3D printing. So it is a possibility, and they have actually printed much larger scaled structures than us.
Okay. Okay, I think you already answered this question, but what is the time gap between subsequent layers? And then we'll have to go to the next speaker after that.
Sure. In this example, actually, I printed it back to back. I went one way and came back instantly because, like I said, once it leaves the vibrating nozzle, it regains its properties of being a no slump concrete and can instantly take the weight of the next layer. In this example, it was back to back.
Okay. All right. Thank you for your presentation.